Before we begin, it is time for a review.
I'll take it from here. Remember, with my approach, we are using the visuals to build our statistical models. And the biggest threat to the models we build is unmodeled effects, meaning that we could model effects, but we failed to. The most common unmodeled effects are interaction effects and nonlinear effects. And to identify interaction effects and nonlinear effects, we have two amazing tools. One is marginal plots that look like this, and they help us to identify interaction effects. And the other is partial residual plots. And these help us discover what we missed, as well as help us to identify what we failed to model.
That was a concise review.
So yeah, that's what I got to say. All right, so we oriented now? So, now, where do we go from here? Good question. Now, at the end of the day, after we've built our model, what we really want to do is we want to summarize the model.
Yeah, I can get on board with that, but how do you do that?
I'll tell you what most people do. Most people use tables like this. And so we see that in this table, there is a curvilinear stress effect, and there's also an interaction between friend ideation and depression. Unfortunately, this table tells us very little. Okay, so we have a nonlinear effect. What's it look like? What is the nature of the interaction effect? I don't know. And the fact that I don't know and I'm a freaking stats genius, that tells you something. That tells you that nobody could possibly know. Actually, it's not just because I'm a stats genius, it's just because you can't get it from this table. There's no way to know the nature of the interaction effect, and there's no way to know what the nonlinear effect looks like. Nor does this table tell us how well our model fit the data, really. Nor does it really tell us how well we've met the assumptions of the model. So in other words, this is kind of a dumb way to summarize a model. And yet, all of science-dom, that's actually punny. Because they're dumb scientists if they report results this way. All of science-dom reports their results this way. It's really stupid. Wouldn't it be better to visualize that? Aye, it would. It would indeed. A better approach is to use visuals because they tell us about model fit, and they also tell us about the viability of the assumptions, and they give instantaneous understanding. You can look at a plot and instantly know exactly what's going on.
Well, now, wait a minute. I can see visualizing simple models like a simple regression, but what happens when you have multivariate data?
It's as if I hire that guy to ask leading questions.
You don't pay me anything.
Yeah, quit your whining. But you do bring up a great point. If you have a simple bivariate relationship, it's easy to visualize it. But when you have multivariate data, you got multiple variables acting simultaneously on one another. So we can't just interpret things in isolation and pretend the other variables in the model don't exist. Like in this model that we showed earlier, we can't just visualize depression. That would be very misleading because depression has an interaction effect. You can't just interpret it in isolation. That's silly. That's silly. So now with that, let me introduce you to the idea of visual partitions. This is terminology that I made up. See the paper linked in the description. Basically what visual partitions are is they are a small collection of plots that can be interpreted in isolation. And this small collection of plots explains the entirety of the multivariate model without bias. If we were to try to summarize this model found in this table, using visual partitions, it would only require 3 plots, even though there are 6 effects. That's crazy! Wait a minute, are you saying you can interpret 6 effects with only 3 plots? By golly, that's exactly what I'm saying. We can fully understand the entire multivariate relationship with just 3 simple plots, and they look like this. And you can interpret these plots in isolation. You can interpret this plot here and say, wow, there is a linear relationship between health and suicide ideation, controlling for all the other variables in the model. Or you can say, wow, look at stress. It has a nonlinear relationship with ideation, controlling for all the other variables in the model. Or you can say, wow, look at the relationship between friend ideation / depression and ideation. And you would see something like this and say, wow. And these 3 plots, well, I guess technically the lower plot is 3 plots combined into one, so maybe it's 5 plots instead of 3 plots, but it's 3 plots. And with this simple graphic, you can understand the entirety of the multivariate relationship. Can you see how much we simplified things? We went from this overwhelming table to this simple graphic that anybody can understand, even the hired help.
Hey, I resent that.
You know I love you. So now, how does one find the visual partitions in a model? There are actually just 3 simple rules for making visual partitions. Number 1, any variable with only main effects can be plotted with partial residual plots, just as simple bivariate plots, as in this image. And of course the y-axis here is the residuals after subtracting out all the other variables. And that's your visual partition for that effect. Any variables that have quadratic effects must be plotted with both their linear and quadratic effects simultaneously, as partial residual plots, like in this example. And this example shows both the linear effect, which is basically non-existent, and the quadratic effect. And then the third rule is that variables with interactions must be plotted together. Again, with partial residual plots where the y-axis is controlling for all the other variables in the model. That's it! Just those 3 simple rules. And you can take a very complex multivariate model and simplify it immensely with just a couple of visuals. But again, before we do that, we need to make sure there are no unmodeled effects. Remember, we are building models from the visuals. Also remember that our biggest threat is missing something in the data, or that there is an effect we could have modeled, but we failed to capture it. So to make sure we have got everything, I'm going to show you a 5-step strategy for finding your visual partitions. Number 1, use loess lines to identify nonlinear patterns, like in this plot. So if you see any sort of evidence of a consistent nonlinear pattern like we have here, then you know you probably need to model whatever is on the x-axis as a nonlinear effect. Number 2, identify interactions with marginal plots. And we've seen examples of that, but I'm going to show you another example, because I'm awesome. No, because you're awesome, and you deserve it. You deserve as many marginal plots as you want. You get those marginal plots. You deserve it. Yeah. Step 3 is to fit a model with the nonlinear and interaction effects from step 2. And maybe test that model using model comparisons, which I'll show you in a minute. Step number 4. Use partial residual plots to perform a residual analysis. And that's what I showed you in the last video, but I'm going to show you again. Because repetition is good and stuff. It helps you learn, I've heard. And by the way, we might be stuck in these first couple of steps and iterate through them repeatedly. So we might find from our residual plot, hey, we missed a 3-way interaction. So then we're going to model it and then do more residual analyses. And then maybe, oh, shoot. Oh, shoot. Darn. Oh, no. I missed a nonlinear effect. Oh, dear. Whatever shall I do? Well, we're going to model that too. And then we're going to do another residual analysis and make sure we've got everything. Simple, simple, simple. Simple as that, dude. And then 5, we're going to visualize the final model with our PRPs, using the 3 rules that I mentioned earlier. Main effects with simple bivariate PRPs. Quadratic effects, we're going to visualize both the linear and quadratic together. And interaction effects, we're going to visualize all the variables that interact together. So, that's it. That's the strategy. Suppose you probably want to see an example.
Well, you have been saying you'd use an example. And yeah, it probably would be helpful.
I'm not going to do that today, honestly. Yeah, figures. I'm going to save that for another day. Hey, I'm back. Oh, you you thought I was gonna wait until the next No, I just had to go to bed, and here I am the next day. Yeah, you didn't have to wait. Hello, welcome to my R screen. So, let's get started. We're gonna start by requiring FlexPlot because we're gonna visualize some things, and we're gonna require Tidyverse because we're gonna tidy some things. And so this right here is just reading in the data set. This is actually a real data set from a real study that was done. This is one of the rare occurrences where I actually use real data. Weird, huh? And so all I'm doing is reading in the data set, and then I am selecting out the variables that I'm interested in, renaming them. And the last thing that I'm doing is I'm just converting religion to a factor, because otherwise some things are problematic if I don't. Like I said, our first step is to just visualize everything together. And so I'm going to look at this plot, and I'm going to be looking for interaction effects and nonlinear effects. And what do we find? Let's see. I'm going to zoom in on this. So when we look at this, what do we see? We see, let's see, certainly a main effect for internet. As internet increases, depression tends to increase, which is what CESD is, by the way. Probably should have told you that earlier. And internet is internet addiction. And so we see that there is generally, the higher your internet addiction, the more depressed you are. And we also see some potential nonlinear effects going on. And it's also possible that there's an interaction with religions. Especially if you look in this far right plot, you see that the slope for religion, or the non-religious people, its slope tends to be much less steep than the religious people. And it's possible that interacts with health. What I'm going to do is I'm going to try to start with a simple model and then use a partial residual plot to see if there's anything that I've missed. So I'm probably just going to start with an interaction effect between internet and religion. And to see what's going on with health, I'm going to have to look at that on the x-axis. So I'll go ahead and do that right now. And if we look at that, we see that on average, if you kind of squint your eyes and ignore the bends, it's not that strong of a relationship, maybe a slightly negative relationship, which makes sense that the healthier you are, the less depressed you are. And there's also potential for some polynomial effects there. So I'm going to start with a somewhat simple model. You might disagree with me. Actually, it's not that simple, but that's okay. So I'm going to model a linear effect of internet, and then a non-linear effect of internet, or a quadratic, and then I'm going to model a religion main effect, and then interaction between internet and religion, health main effect, and then a quadratic of health. And so I'm also going to set up a model comparison where I'm going to try to get rid of the health one. It seems like that might be the easiest effect to dismiss. I'm not even sure it's there, so I'm going to do compare.fits, and it's going to visually compare these two. And what do we see? We see that those two lines are very, very similar, both the full and the reduced. Their predictions are almost identical. So what is that telling us? That's telling us that the full model isn't adding much unique predictive ability. So it's probably not going to pan out that there's a nonlinear effect. But I'm going to go ahead and run a model comparison and see if the statistics support that. And if I look at the top right there, so the AIC smaller value is the one that it favors, so it's favoring the reduced. The BIC is favoring the reduced. The Bayes factor is also favoring the reduced, and the p-value is, because it's not less than 0.05. So it says basically these models are the same. And so when they're the same, you just go with the least complex of the two. And then the R squared is basically identical between the two. So yeah, we have every reason to just keep the reduced model, or get rid of the full model. So yay, that helps. Now I'm also a little uncertain whether that bend in the internet addiction was a big enough bend to worry about. So now I'm going to set up a different model comparison, and I've just tried to leave space. Just try to line these models up as much as you can so you can easily visually see the difference between them. And so the only difference between this full and this reduced model is the inclusion of that polynomial. And if I do a compare.fits of that, I get a plot that looks like this. And once again, the two models are very, very similar. Both the full model in red and the reduced model in blue. So that seems to argue in favor of a reduced model. See what the statistics say, and yeah, the statistics agree. So R squared, I'm only explaining 0.1% of the variance. Bayes factor with a ratio of 15:1 favors the reduced model over the full model. And AIC favors it, and BIC favors it. So yeah, everything favors the reduced model. Cool. So at this point, I might think, man, I am done modeling. I can move on and stuff. But before I do that, I want to do kind of a residual check and make sure I've captured everything in the model. So I'm going to do a partial residual plot. And here I'm putting religion in panels. I'm putting internet on the x-axis, CESD obviously on the y-axis. And model equals reduced, because that's the model that I'm going with. And notice I don't have, in fact, I probably ought to make this explicit, added underscore term equals null. In other words, I don't want to put anything back into the residuals. I want to look at the residuals and see if there's any patterns remaining between these variables. And I'll go ahead and go with the method equals quadratic. And if we look at the plot there, we see that there's still a pattern there. So if we look at the left plot, it looks like it bends downward. And if we look at the right plot, it looks like it bends upward. And remember, we were kind of debating whether we needed to have a nonlinear effect in there. And so when we fit a model without any nonlinear effects, then the residual plots are saying, hey, there's still a pattern here. There's still a pattern of nonlinearity going on. So what the heck is going on here? Didn't we test for that explicitly? Like, we did fit a model where we had a nonlinear effect of, what was it, internet. And the predictions weren't all that different. And so why are we now getting different results from the partial residual plots? Well, the reason is kind of important to explain, and I don't know that I've ever explained this in a video. What we modeled was a nonlinear effect of internet, and we modeled an interaction between internet and religion, but we didn't model an interaction between the nonlinear effect and religion. And so basically what that's going to do is it's going to fit a polynomial that bends exactly the same amount for both religious and non-religious people. And so if we want to allow the model to have different bends for those who are religious versus not religious, we have to change the model. So let me show you how to do that. So now I've got this model that looks very similar to what I had before, but let me make this wider so you can see it all at once. So now what I'm adding is an additional term right there. And so what that is saying is I'm going to model a quadratic effect that varies depending on your religion. So the religious people might have, for example, a concave upward trend, whereas the non-religious people could have a concave downward trend. Without that term in there, the concavity has to be the same between the two religions. And so now I'm allowing the concavity to differ, and the degree of concavity to differ. Or convexity. Concavity, convexity, whatever. Anyway, so now what I'm going to do is I'm going to do another model comparison where I'm comparing a model that has nonlinear effects to a model with no nonlinear effects. So now the second reduced model just has linear terms. So even though it has an interaction between internet and religion, all of those are fixed such that they have to be a straight line. And so if we visually compare the two, we get a plot that looks like this, and now we're starting to see some differences between them. Notice, especially in the tails, we get fairly different predictions between the full model and the reduced model. So there may be something going on here. But let's go ahead and look at the model comparisons. And so the AIC is favoring the full model, the BIC is barely favoring the reduced model, and the Bayes factor is also barely favoring the reduced model. And remember, a Bayes factor of 1 means that it can't tell the difference between the two models. So it's basically saying, I can't tell the difference, but if I had to pick one, I would say reduced. And the p-value definitely favors the full model. So there's a little bit of ambiguity, at least with the Bayes factor. But I'm going to go ahead and, at least for now, go with the full model. And remember, the full model allows for these non-linear effects. So at this point, we've iterated through those middle steps a couple times. We visualized things, we modeled them, we tested them, we did some more residual analysis, made some more modifications to the model, etc., etc., etc. And now we are finally at the point where we feel comfortable. Wait, no, we don't. I forgot the last step. The last step, which is what we already did, but I'm going to do it again. Now I'm going to do another residual analysis where I see if there's any signal left in the data. And so I've put loess lines here. And in the right plot, it does bend up at the right, but that's very common with loess lines. If they only bend at the tails, often that means that there's outliers present. Whereas the plot before, it was kind of a consistent bend, whereas this one is just kind of a bend at the end. So I'm not worried about that. I don't think we're missing any important signal there. And then, so that was with internet on the x-axis and then religion in panels. Let's go ahead and do one where we have health on the x-axis, and then let's look at all the variables together just to see if there's anything that we miss. And so what do we see? We see, for the most part, these lines are flat. Actually, you know what? I have it said to be a quadratic, but I want it to be a loess. So I'm going to do that again. All right, and again, we see bends, but only in the tails, at least in that second row, second column plot, but for the most part, they're all flat. And so at this point, I feel pretty comfortable that we extracted everything we can extract. So that's pretty awesome. And so now at this point, I am ready to do my visual partitions. And so to do so, it's going to require 2 visual partitions. The health effect, because it's not interacting with anything, and also there's no nonlinear effects, so that one's going to be an easy one. We're just going to go CESD tilde health, so we're putting health on the x-axis. We're saying our final model is, oops, that should be full. We should actually, you know what we ought to do? We ought to say full, or final equals full, just to remind ourselves that we have a final model now. So I'm saying, yeah, add the full, or use the full model as to compute the residuals. And what I'm going to do is I'm going to subtract out from the residuals the health effect so that I could see its linear effect. And our visual partition looks like this. Very lovely, except the y-axis has a lot of terms in there. If I had time, I would show you how to fix that, but I don't have time. So maybe another video. But what we are seeing is that basically that's saying that this is depression after controlling for all the other effects in the model, which are internet addiction, religion, and then the nonlinear components and the interactions and all that. So once you control for that, the relationship between health and depression is slightly negative. So the healthier you are, the less depressed you are. Nice. So that is our first visual partition. And now our second visual partition is going to use both internet and religion because they interact with one another. And that shouldn't be reduced, that should be final. And then what I'm going to do is I'll go ahead and make the screen a little bit bigger so you can see all that. So we're adding back the nonlinear effect of internet, the main effect of, I just realized I made a mistake. So I need to have internet in there. So I need to have the linear effect of internet, the nonlinear effect of internet, and I'm putting back in the religion effect, and then the internet by religion linear interaction, and then the internet nonlinear by religion interaction, and then data equals D. And so now if I look at this plot, this will give me a visual representation of what's going on with these two variables together. And so it's actually pretty interesting. So what's going on is that for those who are not religious, the relationship between internet addiction and depression increases gradually, and then it kind of tapers off. That once you reach a certain internet addiction point, it doesn't really make you more depressed. On the other hand, for religious people, it's kind of opposite, that you eventually, there's a very gradual increase in depression for internet addiction, and then about the halfway point, that accelerates. And so the more addicted you are, the much more depressed you get, which is kind of interesting. So yeah, that's pretty cool. Hopefully that gave you an idea of how to use visual partitions to look at our data set and to analyze the data set and to make sure you've captured all the effects that can be captured, and giving you an idea of how you can use a visualization strategy to build models. And with that, that concludes this series on building models from visualizations. Hopefully you found this helpful. And as always, remember, if you want step-by-step guidance with me personally, guiding you through analyses and answering your questions, please visit simplistics.net, where you can take live classes with me. We've got one in 2 weeks from the posting of this video. So you better hurry up. It's gonna be our first live class, May 2024. So I hope to see you there. If it doesn't fit your schedule, you're always welcome to take the self-guided simplistics class. And within the next couple of weeks, we're going to have a mixed models class. Yay! So you can look forward to that. And yeah, that's all I got. Peace out.